Hey, we're a fourth-year EECE team from Cairo University, sponsored by SciVision with a question to ask you. Ever wonder how some of the electronic chips in your devices are made? This is done thanks to VLSI, or Very Large-Scale Integration, a process in which millions of tiny transistors, which are devices that are 40,000 times thinner than your hair, are placed on a single chip. ASIC, or Application-Specific Integrated Circuits, are chips that are built to achieve one specific function. Before you create a chip, you must know what the purpose of this chip is. And the way the chip's hardware behaves is abstracted using a coding-like language called RTL, such as Verilog or VHDL. This part of the design is called the front end. The second part of the design is to translate that abstracted language into actual gates, or cells, made out of transistors. And this is called the physical implementation of the chip, or the back end. Physical implementation is done through two steps. First comes synthesis, in which the designer uses a certain program or tool to translate the RTL into gates and optimize it. Second comes PNR, or place and route, and this stage is made out of multiple mini-steps that slowly create the chip. These are the PNR steps. First, floor planning, where we decide the sizes and area of our chip. Second comes power planning. Since most devices run on a battery or a power source, this step provides the million of transistors on the chip with the power, either coming from the battery or the source. Third comes the placement. Now we need to actually tell the tool to place those gates, while keeping in mind that we want to optimize them as much as we can in order to save area. Fourth, clock tree synthesis. The clock is the beating heart of every digital device, and it's another layer to be connected to those gates. Finally, the routing stage, in which we connect all the gates together into the clock that keeps them alive. We must, however, make sure that our design tries its best to have a fast clock, because a faster clock means a faster device. But we also want to make sure that the area is small and the power consumption is low too. During the design, it's preferred to keep things that have a certain function in a sub-design, which ultimately creates a hierarchy. With that in mind, this introduces different design flows in order to achieve the goals that were mentioned previously. The hierarchical flow, which maintains the hierarchy of the original RTL design physically. The flat flow, which flattens all of the design into a single level. And finally, the topographical flow, which uses aspects from the flat flow but with extra steps that help with optimization. Our project is a comparative ASIC physical implementation of a RISC-V core that was provided by OpenPulp. RISC-V is an instruction set architecture, and an instruction set architecture is a group of instructions that abstract the way a computer or a processor behaves. RISC-V is an open-source instruction set architecture, which means it's free. It's simple compared to other commercial instruction set architectures, modular as it comes with extensions, and stable as there are no major updates for its base instructions. The core's RTL was taken from OpenPulp, which is an open-source, multi-core computing platform. And the RTL has been verified by the senior engineers of our sponsoring company. OpenPulp was chosen due to the reputation in literature reviews, optimized RTL, and optimized resource utilization. Since PULP is short for Parallel Ultra-Low Power, this means that devices using PULP cores consume very little power, which increases battery lifetime. And this comes in handy in applications such as IoT or Internet of Things, which has been an extremely growing field recently. Thank you very much for watching.